Okay, today we're going to look at section 4.2. We're going to start off with a little slow on this section, just covering the basis of sigma notation and summations. What we're going to get to, and it may not appear apparent today, but what we're going to get to is we're going to start finding the area underneath curved objects, and that's what integrals end up being, but we need to set a little of the foundation yet today. So what we're going to start with is sigma notation. What sigma notation is a sum of terms, a bunch of terms, can be written very easily as in sigma notation instead of writing it all out like this. All right, so what we have here, this n is what's called the upper bound. Down here, I equal to 1 is called the lower bound. All right, they give you some function or some equation here where we start with a lower bound. We'll plug in 1 first. And we go all the way until we get to our upper bound, which is up here. So we add all these terms until we get to the upper bound. All right, so we plug 1 in for I, and then we just keep going all the way until we get to n. All right, where I is the index of summation and all this vocabulary stuff down here. So just to give you a little example of what this is, all right, here's a summation here, the summation of I with an upper bound of 6 and a lower bound I equal to 1. Well, we're going to start out with I equal to 1 and work all the way up until we plug 6 in. So we're going to plug 1. We're going to plug 1 in, and we get 1, 2, 3, 4, 5, and we're going to stop at our upper bound, which is 6. So this summation, this whole thing, can be written very easily just by that right there instead of having to write the whole thing out. All right, so down here they want us to do a summation of I plus 1, starting at I equal to 0 and going all the way to 5. So we plug 0 in first, and we get 1, plus, then we're going to plug 1 in, and we get 2. We're going to plug 2 in, we're going to get 3. Plug 3 in, we're going to get 4. Plug 4 in, we're going to get 5. And then finally our upper bound is 5, so we plug 5 in, and we're going to get 6. Okay? Now notice there is multiple ways. This down here is actually the same as this. There's multiple ways to write two summations. Those are just two different ways to write that same summation, just different upper and lower bounds. All right. Moving on here. Here we have an upper bound of 7, and we're starting with our lower bound of 3. So we're going to start at 3 and plug 3 in. So we're going to have 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. And we reach our upper bound and we're done. And the last one here, it says down here, let me move this for you. It says I equal to 1 as our lower bound. We're going to n. So wherever we see I, we're going to start with 1. We're going to go all the way to n. So we're going to have f of x 1 times change of x plus f of x 2 change of x plus dot 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 all the way until f of x n change of x. All right. A couple rules for summations, and that they have the same rules as limits. If we have a constant, we can pull that constant out in front. And so what they have a constant of k here, and they pulled it out in front, and then we can take the summation without the k and without the constant in there. And the same thing, if we have 2 added together, we can take the summation of the first and add it to the summation of the second, or subtract it from the summation of the second. Either way. All right. And notice they both have, when we do them separately, they're both going to have the same upper. Here's your upper, and here's your lower bound. They're both going to have the same upper and lower bound. Okay? Some summation formulas that we're going to need to know. It's going to make a little life easier for us when we get to some problems like example 2 down here at the bottom. Is a summation of a constant is just a constant times our upper bound. Because if you think about it, it's saying we're going to add this constant together as many times as what our upper bound is. So I can give you an example of the summation of I equal to 1, and we're going to 5 of 2. All right, we start with 1, we plug 1 in for I, and we get, well, there's nowhere to plug it in, so we get 2 plus 2 plus 2, all the way until we do it 5 times. Well, instead of repeating addition, we might as well multiply. We learned that way back in 5th grade, okay? So the summation of a constant is just the constant multiplied by the upper bound. All right, the summation of just I can be broken down into this formula down here, n times n plus 1 over 2. The summation of I squared can be broken down into n times n plus 1, 2n plus 1 over 6, and then I cubed can be broken n squared, n plus 1 to the quantity squared over 4. I remember back in college I had to prove all these and stuff like that. I'd show you, but we're going to run out of time. Maybe someday I'll show you. Okay, example 2 here. Evaluate the summation of n, I equal to 1. So our lower bound is I equal to 1, our upper bound is n. And we're going to evaluate I plus 1 for n equal to 10, 100, 1,000, and 10,000. Well, you may be thinking, whoa, that looks crazy. But we're going to use our rules and our formulas up here to simplify it for us. All right, so we don't have to do all the summations for that. All right, so we're going to simplify it. If you notice here, I can pull an n plus, or a 1 over n squared out. So I can write the summation of n I equal to 1, and I can pull a 1 over n squared out, and I'll have just left over this I plus 1. When we're doing problems like this, we want to get it just so we have i's and stuff that we can deal with and simplify, so we can get rid of our summations. Notice these give us nice little equations where we get rid of our summations, so we don't have to deal with those. All right. So now we know from our rules of summations over here, I'm back over here again. Now we know from our rules of our summations that we can do these separately. So we can do the summation of I plus the summation of 1. And our upper bound is going to be n. Our lower bound is going to be I equal to 1. I equal to 1. And we still have that times our 1 over n squared. All right. So then I'm going to look, all right, let's simplify. The summation of I equal to 1 and an upper bound of n is right here. So we know that this summation is going to be n times an n plus 1 all over 2. And then we know that this summation, this is just a 1, by the way. This summation is right here. It's just a constant, right? A constant, and so we just said our constants times the upper bound. Our upper bound is n, so this summation becomes n. So it's very nice. We just got rid of all our summation stuff, and we're just dealing with n's, which is good because we need to evaluate for n equal to 10, 100, 1,000, and 10,000. So let's just simplify is all we need to do. Get a common denominator of 2. So this would be 2n. So I'll have 1 all over n squared times, let's see, n squared plus n plus 2n would be 3n all over 2. And let's multiply through. Let's bring my n squared back in. So let's go n squared plus 3n all over 2n squared. And notice, since every term has an n in it, we can cancel one n out. Since every term has an n in it, we can cancel one n out. So this can become a 1. This can become a 1. And this can cross out. So what we're left over is our very simplified form is just n plus 3 all over 2n. And then we can evaluate 10, 100, 1,000, and 10,000. I'm not going to do that. All you need to do is, I don't know, plug it in your calculator. You plug 10 in for n. So you have 13 all over 20. Okay? And then you do it for 100. You do it for 1,000. You do it for 10,000. And that's all that is right there. Remember, when we're doing problems like this, you want to get it so where we just have an I or an I squared or an I cubed and maybe a constant just to make life easier on ourselves and get rid of the summation. That's the trick to those problems right there. I hope this helps, and we'll see you in class tomorrow.